Are we live? Yes, we are. Hi guys. So this time I just wanted to kind of showcase where I'm at with vision transformer model. It's not really a VQ-GAN. I guess kind of similar. Just working on the Faces 128 dataset at the moment, trying to get the best reconstruction quality possible. And basically I'm using an encoder that feeds into a soft VQ-VAE with transformers, vision transformers, and then a convolutional decoder reconstructs the image. So the encoder starts with a patch embedding. It just splits up the input image to 4x4 sized patches. We have 5 input channels because I embed the position X and Y concatenated to the 3 RGB input channels. So yeah, this will be the shape, height and width divided by patch size, and converts to the latent space, the number of output channels. Simple MLP with 2 linear layers here and the GALU activation. Now the hidden dim, this is basically D. We could say it's D, but let's keep it dim. It could be basically anything. But it projects up because hidden dim is usually larger, like 4 times the input dim, performs a nonlinearity and then projects it down. And I have a multi-head attention here. Pretty standard. I don't use a mask because it's used for images, so no causality here. And a standard transformer block. Here MLP dim scale is basically the upscale dimension that I mentioned in the at the MLP. This is just a placeholder because it's the same. I think I don't even need this. So the encoder itself, as I said, as the position embedding first, no cosine, etc. here, just I'm creating coordinates for each pixel and concatenating it to the input channels, and then create these 4x4 patches with latent dim channels for each patch. From then on I reshape the input from BDHW to BT or BND and run the transformer blocks n times n transformer blocks on it. And then I convert it back to the original shape. So in the end this will be a grid and in this shape basically. Oh. And the decoder, I didn't use transformers yet. I just went with a very simple conv transpose for upscaling, and I added a normal convolution here that keeps the size just to be able to store more data via these parameters. Normalization, ReLU, standard. And so this so ZQ it, comes from the soft VQ VAE, and so this is a patch of T by 16 by 16. Not exactly, I think we will run it and see what the internal shape or the size of the grid is. I guess it's 32 by 32 because the input image is 128 and the patch size is 4. So this doesn't apply. And so this is just one block here. And I use a GAN based loss. So here's a simple discriminator. I haven't yet got this to work perfectly because the discriminator learned much faster, and then after a while it just rejected all the fake images, meaning the training after this convergence happened, it deteriorated and started to diverge. So I'll try to fix that now. And this, well, it returns a one channel output, basically to signify how true that image is. So a number treated as a probability or just a number, one is being that the image at that patch is true, and as it goes towards 0, then it means it's less true, so more fake. So a simple discriminator here. And yeah, as I said, 32 by 32 grid of latents. So here's the soft vector quantizer with a continuous latent space, just a uniform init for the codebook. I think I could, because I'm using transformers in the encoder, the uniform init isn't so great. Now this time I could pick the outputs from the encoder and probably start with that to achieve a higher perplexity. That's something to do, or I will try. Yeah, this is the standard part for any VQ-VAE, and the soft VQ implementation starts here. Just subtract the minimum distance from the dists. This is distances squared, by the way. And then we convert them to logits using this temperature parameter tau. In the paper this was 007. I adjusted it to 1, but let's write it back. So we perform a softmax on these logits, and this means that for all input vectors we will have probabilities created, and when multiplying, the ZQs will be the expected value of these probabilities. But it's basically just, so the expected value is basically just a sum of x by the probability of x. So it's basically a linear combination of these. So each ZQ is a linear combination with different coefficients, called probabilities of these codebook vectors. And since this works with probabilities, we don't need to perform one-hot encoding and calculate it for the perplexity like in the standard VQ. We can just take the mean, and with the Shannon entropy exponentiated, we already have the perplexity. And just convert it back to the original shape, the ZQs here. So this is the model itself, with encoder heads and encoder. This annotates the transformer layers. And now here in training, here's the discriminator, and of course two optimizations, or optimizers, sorry. And now I train it. So first train the discriminator. This was the part that went pretty fast. I used binary cross entropy, and after the discriminator was trained well enough, it just started to diverge, as I said. So now I changed it to this loss, just d fake dot mean minus d real dot mean. I'm about to try this, and this changed as well. So I use an F1 or an L1 loss and the structural similarity index averaged over the batch. So a perfect score for this is 1, so we just kind of negate it. And the total loss of G is, with this alpha, we multiply the adversarial loss and the reconstruction loss. It worked pretty well, but I want to make it much better. I think it has much more potential. Now, right away, I only used a single grad scalar. I'm not sure yet if this is sufficient enough, but I'm gonna have 2, I think, because and it probably keeps the state, so this could be one thing why my model didn't work as well. So I have scalar G and scalar D separately for the generator and the discriminator. Also, perhaps I could move the optimizers here, and I could tune the learning rate with the scheduler. So let's do that. And we'll have 50 epochs. Now for this, for the previous training, I used 4 transformer blocks. I lowered it to 2 because training was pretty slow, and I have a feeling we can achieve almost the same result with less layers. Also lowered the learning rate from 4 to 3e minus 4. And this becomes scalar D, this becomes scalar G. All right, let's wipe the GPU RAM, rerun everything, and it's a small model, but due to the patch embedding that I'm not using a convolutional encoder anymore, which reduces the size, but instead 4x4 patches, and directly feed those to the transformers. I had to lower my batch size to 32, which affects training speed, as it means more memory copies during training. But I have 16 G of VRAM. So let's see how it trains now. The SSIM also takes a while to calculate. So even the first model evaluation that calculates the initial loss took like 20 seconds. Now the train loss D is minus. So that's strange for me. I'm just trying this for the first time. I'm not... Okay. So the fake is what the model predicts. So we are just gonna see if this even converges anywhere. But I don't like these values. So this is supposedly the VQ-GAN loss, and VQ-GAN GP model also introduces a gradient penalty, which I haven't added. But of course this makes no sense at all. Just like, I don't know, the minus loss here is weird as F. Should probably change the discriminator. To the VQ-GAN discriminator. Yeah, so this is just complete BS. I like the binary cross entropy way better. At least it converges somewhere. So in order for this to work, so loss D is negative, because for D fake, so this part is bigger. I will just revert this to the binary cross entropy, or just read the VQ-GAN GP paper. This is a newer one. Alright, so this is kinda today or tomorrow's work. I wanted to continue with GANs, with normal, then Wasserstein, then probably implementing this. However, I had an idea about how I could maybe improve transformers dynamically. So now I will just get this to work with the binary cross entropy and tweak my transformer implementation. So I don't want this live to get boring. I will check in next time when I got something perfectly working.